This video is going to build on the last thing we did, which was looking at ionic bonding and how atoms can join together to form compounds by ionic bonding, by giving and taking electrons. So if we were to go back a few pages, we would see sodium chloride on page 30. We did our bonding diagram. Here's our sodium ion over here, and here's our chloride ion. The sodium, when it's in its atomic form, its elemental form, it has 11 electrons, so 1 on its outer shell. It gives that electron to the chlorine that has 7 electrons on its outer shell to form the chloride ion. Thus, they both get a full outer shell of electrons. Now, when that electron is moved across, the sodium atom becomes a sodium ion. It ends up positively charged, and the chlorine atom the chloride ion ends up negatively charged because this electron is negative. Now, those opposite charges will stick together, and that is our ionic bond. I suppose it should really be called an ionic attraction. Okay, now if you remember right back to the very beginning of chemistry, I'd have said to you, how many sodium atoms? If I gave you enough sodium atoms, how many sodium atoms would it take to cover a full stop? And the answer was, you don't need to know this. It's just a little pub quiz question, really. The answer was this number here: 4,000 million, 4 billion sodium atoms to cover that one full stop. So what I'm trying to say is thinking about ionic bonding in terms of one sodium atom giving one electron to one chlorine atom is quite laughable, because even the smallest, most minuscule amount of sodium and chlorine reacting together will be billions of atoms forming billions of ions. So we need to think about this in a bigger scale. And that's where we come on to with this video. We're thinking about some of the physical properties of sodium chloride. So this sodium ion here might have been this sodium ion here, and that chloride ion there might be that chloride ion there. So we've got this sodium ion attracting this chloride ion. But of course, there's going to be other sodium ions. So we might have another sodium ion here, another Na plus there. Okay, now that sodium ion there may have given its electron to this chloride ion here. Okay, now that positive ion there is also going to attract that negative ion there. It doesn't matter that who they give their electrons to, it's what they end up as. They end up positively and negatively charged. And so what we're going to do is all these billions and billions of sodium ions and chloride ions are going to end up arranged so they attract each other. And it's going to be alternate, okay? Because like charges repel and opposite charges attract, opposites attract. So we can fill in this this matrix, if you like. These are just grid lines, these black lines here. They're not actually any sort of bond in themselves. They're just to help us draw the arrangement. We can fill in this grid-like arrangement on each of these nodes, these joins, if you like. We are going to write an ion. So this is a negative ion here, so this would have to be a positive ion here, an Na positive. If that's negative there, that has to be a positive there, so an Na positive. And that's next to the negative there. So there, that positive, that would have to be negative. And you can fill in this whole thing with oppositely charged ions. And what we end up with is a regular arrangement. A regular arrangement is a neat arrangement. Okay? And what we end up with is a cube-like arrangement. Okay? Now this arrangement is called an Ionic lattice, and that's important. Okay, it's a regular and neat and tidy arrangement of alternating positive and negative charges. And you can fill in your own book in the way I am here. Okay, you get the idea? It's opposite charges regularly arranged. So the question, do you think, let's label that an Ionic lattice. Important, we need to know that term. Do you think ionic substances like sodium chloride have high or low melting points? Explain your answer. Okay, well, whether it has a high or low melting point depends on how easy it is to separate these, because particles in a solid, if you go back to year 7, you were told particles in a solid were all arranged in a nice, regular, ordered manner, and as you heat them up, they vibrate more until they can break apart from that arrangement into the liquid arrangement, which is chaotic, and the particles can move over one another. So there is a liquid and there is a solid. Okay, and the difference between that and that is the organisation. Nice, neat, regular, ordered arrangement, chaotic arrangement where the particles move over one another. Well, if something has a high melting point, it takes a lot of energy to break them apart. If something has a low melting point, it takes a little bit of energy. Now, what we have here holding these particles in place, these ions in place, are opposite charges. And that creates a force of attraction. That creates a strong force of attraction. Imagine this was a skip full of magnets and your job was to separate them. It would take you hours and a lot of energy. Now imagine you have a skip full of, say, ping pong balls, which aren't attracted to each other. And your job was to separate those. Well, that would be easy. You just shovel them out there. They'd move apart because they weren't attracted. What we have here are strong forces of attraction. And that's really, really important in saying whether this has a high melting point or a low melting point. So do you think ionic substances like sodium chloride have high or low melting points? Explain your answer. They have high melting points. Why? Okay, it takes a lot of energy to overcome the strong forces of attraction between the oppositely charged ions. Okay, so we have to know about melting points and we have to know about whether the substances conduct electricity. Okay, so to understand whether something conducts electricity, we have to know what a current of electricity is. Now, if you speak to most GCSE students who've listened very hard in their physics lessons, they will tell you it's a flow of electrons. And they're not wrong, they're just not totally right. And if they'd listened to their physics teacher more carefully, they would have heard their physics teacher say a current of electricity is a flow of charged particles. Now, most of the time when we're in physics, the charged particle that is flowing is an electron. And that's why metals conduct electricity. They have delocalized or free electrons that can move. And of course, we are normally using metals to conduct electricity in everyday life. But electrons are not the only charged particles. What other charged particles do we have? Now, somebody's going to put their hand up in a minute if this were a classroom and say protons, because protons are positively charged. And that's right, but the protons are locked in the nucleus and they never move. So that's not right for currents of electricity. But what we have here, of course, is we have ions. Now, what is an ion? An ion is a charged particle. So electricity can flow if the ions can move. So a flow of charged particles is either a flow of electrons or a flow of ions. The question now says, look closely at the ionic lattice above and explain whether solid sodium chloride can conduct electricity. So to answer this question, you have to ask yourself two questions. 1, are there any free electrons that can move? 2, are there ions that can move? Okay, let's deal with the electrons first. Well, if we go back to our bonding diagram from the other lesson, we can see all the electrons are used in bonding. There are no spare electrons. So let's write that down straight away. Solid sodium chloride, so solid ionic. 1, no free electrons, all used in bonding. 2, are there any free ions that can move? Well, there's lots of ions. So 2, ions are present. But what's the current of electricity? A flow of charged particles, and we're looking at a solid ionic here. Well, can these ions flow? The answer is no. They are locked in place by these strong forces of attraction. So ions are present, but cannot move. So the only conclusion is, with solid ionic substances do not conduct, because there's no free electrons and there's no ions available that can move. Right, now it gets a bit more interesting, because now we start saying to ourselves, oh, how can we make those ions move? Well, the answer is we turn it into a liquid state. because when it's a liquid, the ions can move. So how can we turn it to a liquid state? Well, we heat it up and we melt it. Okay, melt it. Heat it up, and now that would conduct electricity because the ions can move. But that sometimes, we've already heard, haven't we? Melting it, the melting point is high, takes a lot of energy. Can we make sodium chloride a liquid another way that doesn't involve melting it? The answer is yeah, just go to the seaside. Okay, because salt, sodium chloride, dissolves in water. Okay, dissolve it. When it's dissolved, it's in a liquid state. Explain whether sodium chloride in a liquid state can conduct electricity. Answer, yes. There are no free electrons. Let's be clear about this. No free electrons. Okay, so many times I say to students, can ionic substances conduct electricity? They say, yeah, there's free electrons. No, there aren't. That's nonsense. Okay, yes. Why? Because the ions, and the ions are, of course, charged atoms. A definition of an ion, a charged atom or a group of atoms, because the ions are free to move. So, ionic substances will conduct electricity in the liquid state. How do we get them into the liquid state? We melt them or dissolve them. And that's what we need to know about ionic substances.